Hi, I'm Justin Kong,
And I'm Mario Kosla.
and today we'll be discussing the use of Beer's law to find the concentration of an unknown solution.
So, the background of this experiment. Beer's law states that absorbance is proportional to the concentration of light-absorbing molecule. So, the changes in absorbance for slight changes in concentration will show the greatest differences. And the point where molecule-absorbing light absorbs the most intensely is called lambda max. So lambda max for any light-absorbing molecule is equal to the wavelength of the maximum absorbance. After lambda max is determined, a Beer's law plot is created by using the absorbance at that lambda max while concentration is varied. To continue the background, Beer's law only works for dilute solutions because when the concentration is too high, the solution becomes too dark for any light to pass through to the detector, and therefore all absorbance becomes 100%, regardless of how much light is absorbed, because the detector thinks that all of it is being absorbed. And there are many uses of Beer's law in today's world, such as in quantitative spectroscopy, in the brewing of chemical solutions, which is relevant to the FDA.
So the purpose of the lab is to use Beer's law to create a plot of absorbance as it varies with concentration of cobalt chloride hexahydrate. And also it's to use the Beer's plot of known concentrations of cobalt chloride to determine the concentration of a solution of cobalt chloride of unknown concentration. The hypothesis of this experiment is that linear dependence of absorbance on concentration of solutions of cobalt chloride.
Now let's move on to the methods. Here's a diagram depicting the spectrometer used in the experiment. So on the left side there's a light source, and on the right side there's a detector. And in the middle, one can place a sample cuvette, and the machine measures how much light passes through that cuvette. So now, using a solution of 0.1 molarity cobalt chloride, the maximum absorbance of light ranging from 400 to 700 nanometers was determined, with 30 nanometer increments. After lambda max has been determined, the absorbance of a series of solutions of cobalt chloride ranging from 0.08 molarity to 0.02 molarity was determined at lambda max to create a Beer's law plot. The absorbance of the solution of unknown concentration of cobalt chloride was recorded, and it was compared to the Beer's law plot. Because the Beer's law plot is a linear relationship, the concentration of the solution of unknown molarity can be determined by drawing a line directly from the absorbance down, dropping a perpendicular line down to the concentration on the x-axis. So here are some pictures depicting the setup of our lab. So on the left we have a picture of the spectrometer used, and as I explained earlier, this basically measures how much light passes through a sample of liquid.
On the right, we have two pictures depicting the different concentrations of solutions that we made. But before a plot comparing concentration and absorption can be made, the various dilute solutions had to be made. And this was done by taking a certain volume of cobalt chloride solution with a known amount of aqueous cobalt chloride and mixing it thoroughly with distilled water to create specific dilute solutions. So overall, the concentrations of the unknown solution were relatively inconsistent, as a standard deviation of 0.00461 molarity was about 10% of the average molarity of 0.0457 molarity. The median of the concentrations was 0.0450, slightly less than the average, suggesting that there was some unusually high values which skewed the data, such as 0.0624 molarity, which was unusually high. The experimenters found concentration of 0.0451 molarity was relatively accurate in comparison to the average concentration, with a percent error of only 1.31%. As seen in the histogram, most of the data is clustered between a concentration of 0.043 molarity and 0.0469 molarity, and also the shape of the histogram is approximately a bell curve.
So now moving on to the experimenter's data, a graph depicting absorption at various wavelengths was created. As can be seen from the image, the maximum absorption, lambda max, was around 510 nanometers. Because the solution absorbed hardly any photons of 600 to 700 nanometers in wavelength, it appears red to the human eye. This value of 510 nanometers was used in part 2 of the experiment to create a graph of absorption versus concentration for various concentrations of cobalt chloride solution. The experimenters compiled this data and found a line of best fit. Finally, the unknown concentration, the red point on this graph, was found to be approximately 0.0451 moles per liter.
Now moving on to the error analysis of the experiment, the experimenters found two possible sources of error. The first possible source of error, which stems from the materials, is the saturation of the hydrate cobalt chloride. If the hydrate cobaltous chloride hexahydrate is not saturated with water, then the molar mass of the hydrate will drop to an extent which the experimenter will not be able to calculate. Therefore, the unknown concentrations will actually be larger than they actually are, as a higher mass of cobalt 2 chloride will be in solution than previously thought. A second source of error is the actual concentration of the solution. If the concentration of a solution is high enough that the solution becomes opaque, then Beer's law is ineffective. Beer's law, as previously stated, only works when a solution is transparent so that the amount of photons absorbed can actually be measured.
So, moving on to the conclusion of this experiment. So, the chemical analysis involving Beer's law showed two things. First of all, it showed the lambda max value for the cobalt chloride solution to be approximately 510 nanometers. It showed a second thing. Upon completion of the experiment, the concentration of the unknown solution was found to be approximately 0.0451 molarity. By looking at the experimenter's data and the class data, Beer's law in this experiment tended to have a decent level of precision and accuracy. However, this experiment was prone to various errors which skewed the data. Many times, the least squared regressions line for a set of different concentrations had a high correlation within its own trial, but when compared to the other data from separate trials, the results often varied.
For future experimentation, more work could be done using more accurate and precise tools such as the large mechanical pipette. Also, further work could be done to determine at what concentrations do Beer's law not apply, and to see if solutions of different elements have the same maximum concentration.
Finally, we would like to acknowledge Ms. Zismore for providing us with all the materials and information necessary to carry out this laboratory procedure. Thank you very much for listening to our lab.
Thanks.
Bye. Okay, good.
Alright, do you need me to make the video?